What's up, everybody? John the Morgile here. Going to do a quick, well, maybe not so quick video regarding the speed of light. So basically what my research is showing is that the figures that we get for the speed of light are pretty much the definition of pseudoscience, because you start with this cockamamie experiment way back in the 1800s, and it's regarding the transit of one of the moons of Jupiter. This guy believes he can measure the speed of light by the time it takes for the light to go bounce off Jupiter and come back. And we'll get into it in a little more detail, but you know, he didn't even believe that he knew the distance to Jupiter, didn't claim to know that, or if he did, it was obviously wrong. Any figures that they would have put in a heliocentric layout would have necessarily been wrong, even if it was a heliocentric in reality, but it isn't. So anyway, let's get into this in a little detail, because it just seems like that original cockamamie experiment was sort of the yardstick for the speed of light. And it just seems like the more you try to test with this assumption, the more you find that the speed of light couldn't possibly have been anything close to what he believed that it was. You know, his figures would have necessarily been way off, because he was considering Jupiter to be some millions of miles away, but he would have been necessarily wrong. And to use that as the yardstick and even go around changing the definition of what is a meter, because the meter is apparently defined by the speed of light or something to this effect, and so they would literally go back in and change the definition of what is a meter until they finally decided on something that was pretty close to even that original half-baked attempt using the moons transiting Jupiter, Jupiter's moons transiting it apparently. Well, we'll get into the figures here and everything, but this is sort of the background, because when you actually get into it, it is just sort of astonishing how ignorant theoretical physics is, because the tests that they use, ranging the good old Leon Focault has a hand in this again, and of course Focault is famous for the pendulum experiment amongst others, but Foucault's pendulum supposedly proves that we live on a spinning globe. However, that's of course ridiculous. It proves that the ether is in motion above a stationary Earth, and you see things like when eclipses happen, apparently Foucault pendulums will reverse their direction or stop during solar eclipses, and they in no way align to the idea or prove the notion that the Earth is spinning on an axis. It's quite funny that Focault has a hand again in originally sort of confirming or fine-tuning the values that were originally garnered by Olaus Romer in 1676. So let's get right into it. This is an article from math.ucr.edu, so this would be accepted globe Earth heliocentric science, and again, this is regarding how is the speed of light measured. I'll put a link in the description. Before the 17th century, it was generally thought that light is transmitted instantaneously. This was supported by the observation that there is no noticeable lag in the position of the Earth's shadow on the moon during a lunar eclipse, which would otherwise be expected if c, or the speed of light, were finite. So just pausing from this article or document real quick, isn't it funny that the example they would give here is no noticeable lag on the Earth's shadow on the moon, right? So this is first assuming that it is the Earth's shadow on the moon, which it couldn't possibly be since it is a stationary plane Earth, and you have things like the selenelion where both the sun and the moon are visible in the sky during lunar eclipse. So to somehow assume that they know how far the moon is, which in the heliocentric theory they're way off by probably hundreds of thousands of miles, because they claim that the moon is 240 some odd thousand miles away, and that is absolute nonsense. It couldn't possibly be that distant, and that is demonstrable. Don't have to get into that. Did see a beautiful crescent moon last night, and I'll put up a slide. Yesterday was Tuesday the 20th, and as we can see, slight crescent moon, and many hours after sunset, which is geometrically impossible assuming the heliocentric theory. So according to the heliocentric model, we're looking at a top-down view of the Earth and the ecliptic plane. So, hypothetically, we're looking down on the ball Earth from above the North Pole. Allegedly, the moon orbits the Earth along the same plane, more or less, that the Earth allegedly orbits the sun. So this top-down two-dimensional perspective is adequate. You could just bear in mind, however, that the moon's orbit supposedly positions it on a plus or minus 5-degree offset tilt from the ecliptic plane. So if you were to, say, turn this image 90 degrees, so you're looking at it from a side view, then you would have more or less two planes. You'd have first the ecliptic plane, which I'll define as a red line. We'll make it thick enough so you can see it. And allegedly, this would be the ecliptic plane that the Earth revolves around the sun upon. So we could put a very small sun in the center of that, hypothetically, and then put the Earth revolving around the sun on the ecliptic plane. We'll make that a bit smaller. Oops. And of course, we'll make it nice and blue. Now, allegedly, the moon orbits the Earth along more or less the same plane, although it's tilted a mere 5 degrees. So again, this would be like a side view. This is an exaggerated angle. That's obviously more than 5 degrees, but just to give you an idea of how that would look from the side view, make it a darker color. That angle would be 5 degrees, representing the moon's alleged orbit. But again, looking at it from a top-down view is adequate, and so just get rid of these, get them out of the way. The other night I was able to see the crescent moon after sunset. So if I'm on this ball here, and everything, we're supposedly spinning counterclockwise if you're looking at it from the top down above the North Pole. And so if I'm on this ball going around it, and the sun sets, meaning I'm past this terminator line, past the twilight zone as it were, my line of sight is going to be tangent or divergent from the curve of the Earth. So if I'm on the ball after sunset, my line of sight could be described as a line similar to this. Make it red so we can see it. Now, the problem is, again, we know based on the heliocentric layout where the moon should be in its orbit just by looking at the phase of the moon. And as you can see on this diagram, the full moon would be 180 degrees from the sun, or on the opposite side of the Earth as the sun. And the no moon phase would place the moon more or less aligned to the sun. And what supposedly gives us solar eclipses is when the moon is aligned to the sun on the ecliptic plane as well. We don't need to get that complex into it. Again, if my line of sight is described by this dotted line as a tangent to the curve of the Earth, and the crescent moon is definitely going to be somewhere on the day side of the Earth over here, how is it possible for me to see the crescent moon overhead when I'm on the night side of the Earth? Like I saw the other night, a crescent moon, maybe 6 to 10% illuminated, and it's physically impossible to get a glimpse of the moon overhead after sunset, the crescent moon overhead after sunset, because it should be way over here. So how am I looking at a crescent moon overhead over here on the night side of the Earth? The same thing goes for lots of observations of the full moon during the day. Again, the full moon is supposedly necessarily 180 degrees opposite the sun relative to the Earth. So we've all seen full moon during the day. So if you're on the day side of the Earth, and again, your line of sight is going to be tangent to that curve once the sun is overhead, how is it possible to see the moon up here in the day side of the Earth when it should be way the heck down here on the night side of the Earth? For heliocentrists to claim that they know the distance to the moon or any of the planets is abject nonsense. And, again, that is demonstrable since the Earth has no curvature, nor is it in motion. Then that means that the moon is definitely a local object. It's not hundreds of thousands of miles away. And so to assume, and to assume that the sun is some 90 or 100 million miles away is, as a unit of measurement, the planet Earth to the sun, in theory, in the heliocentric theory, that's one astronomical unit, right? And so to use just totally a fallacious, non-realistic starting point and measuring stick to assume that you're somehow going to glean an accurate measurement of the speed of light using that measuring stick is preposterous. And furthermore, what is preposterous is to take ancient experiments and use them as your standard goal target number in terms of the speed of light. I just wanted to quickly mention that it is well known that the speed of light decreases as it travels through higher density media. So light travels apparently much more slowly through water than it does through the air, or hypothetically through a vacuum. However, again, I disagree with the fundamental notion that light is some type of particles traveling through the media in a wave form, in the form of photons traveling, physical little particle objects traveling through media. It just doesn't sit well with me for some reason. It doesn't seem very realistic. Furthermore, being able to accurately measure the speed at which light travels, if light isn't tiny little photons traveling through media, as I don't think that it is, then to measure the speed of that is quite ludicrous. Let's continue with the article here. The moon during a lunar eclipse, which would otherwise be expected if C were finite. Nowadays, we know that light moves just too quickly for the lag to be noticeable. Galileo doubted that light's speed is infinite, and he devised an experiment to measure that speed by manually covering and uncovering lanterns that were spaced a few miles apart. We don't know if he ever attempted the experiment again, but again, c, or the speed of light, is too high for such a method to give an even remotely accurate answer. And I would say I agree. Continuing, the first successful measurement of c, the speed of light, was made by Olaus Romer in 1676. He noticed that depending on the Earth, Sun, Jupiter geometry, there could be a difference of up to 1,000 seconds between the predicted times of the eclipse of Jupiter's moons and the actual times that these eclipses were observed. So just reiterating that real quick, this is claiming that in 1676, this character Romer noticed this peculiarity of 1,000 seconds, which, just to be sure, 1,000 divided by 60 would be, yeah, 16.6666 minutes. So we're talking 16 minutes and 40 some odd seconds. So supposedly they're calling this a correct measurement. They're saying he correctly surmised that this is due to the varying length of time it takes for the light to travel from Jupiter to Earth as the distance between these two planets varies. Wow, a lot of assumptions going into this measurement of the speed of light, isn't it? Okay, so he obtained a value of speed of light equivalent to 214,000 kilometers per second, which was very approximate because planetary distances were not accurately known at the time. And I would add that planetary distances are still not accurately known, and the claims that heliocentrist theory proponents have in terms of the distance is just abject nonsense. It couldn't possibly be. If you look at the inner solar system, the planets Mercury and Venus are so distant on average and so small in terms of their actual physical diameter, you would never be able to see such planets from millions and millions of miles away. It's just physically not possible. That's not how light or optics work. The light waves, assuming the heliocentric theory, which is just asinine, would fizzle out or attenuate into the background radiation or frequency of space theory. And of course, we should never achieve a line of sight towards the inner solar system after sunset, as described in these diagrams. Again, our line of sight should be tangent to the curve of the Earth, and so after sunset, looking towards the horizon, would be looking towards a divergent angle away from the inner solar system, divergent from that line of sight. So again, they're calling this completely absurd quote-unquote measurement of the speed of light more or less correct, because the distance between these planets is different. He can somehow measure the 16 minutes where the transit should occur and the 16-minute lag. That's supposedly going to help them measure the speed of light, which is just, I mean, if you think about this for 10 seconds, it's preposterous. Okay, but their experiments get much, much better, I will tell you. Right. So anyway, at least they do admit that the planetary distances were not accurately known at the time. Again, that was in the late 1600s, apparently. And I would add that they still don't have accurate distances to the planets, and certainly not the heliocentric values. So continuing, in 1728, James Bradley made another estimate by observing stellar aberration, being the apparent displacement of stars due to the motion of the Earth around the Sun. So here goes another one where they're assuming a heliocentric theory and all these great many millions of miles involved that are just theoretical nonsense, and using that as a measuring stick to somehow measure the speed of light, which again I would say is just absurd. I mean, this is the pinnacle of pseudoscience. So in 1728, James Bradley made another estimate by observing stellar aberration. So what is stellar aberration? And according to Wikipedia, the be-all, end-all source of truth, stellar aberration is an astronomical phenomenon which produces an apparent motion of celestial objects. It can be proven mathematically that stellar aberration is due to the change of the astronomer's inertial frame of reference. And the formula is derived with the use of Lorentz transformation of the star's coordinates. So, As you can see, this is all based on a lot of theory about what the stars are, how far away they are, and the notion that the Earth is in motion, the stars are in motion, and the Earth is in motion, and everything's in motion, which is, again, absurd because the Earth is demonstrably at rest. The Earth isn't in motion whatsoever. So, continuing on with this sort of tangent, what is inertial frame of reference? So inertial frame of reference in classical physics is a frame of reference in which bodies whose net force acting upon them is zero are not accelerated. That is, they are at rest or they move at a constant velocity in a straight line. In analytical terms, it is a frame of reference that describes time and space homogeneously, isotropically, and in a time-dependent manner, or time-independent manner, rather. Conceptually, in classical physics and special relativity, the physics of a system in an inertial frame have no causes external to the system. An inertial frame of reference may also be called an inertial reference frame or inertial frame, Galilean reference frame, or inertial space. So, in other words, this is all assuming that, yes, the certain bodies can be considered at rest if they're both moving in a constant velocity in a straight line, similar constant velocity in a straight line, which, granted, if you're talking about objects in a vacuum hypothetically traveling in straight lines without any cause for acceleration, then they will continue as such. But to claim that objects in motion around a giant curve around the galaxy, around a giant curve around the sun, around a giant curve around the Earth, in the case of the moon, in theory, that is anything but straight lines. That is conflicting curvilinear parabolic trajectories at varying velocities, arcs of travel. I mean, you're talking all kinds of motion that is not in a straight line. Apparently the Earth and especially the Moon are supposedly traveling in multiple conflicting directions simultaneously at varying accelerations, because anytime you travel around a curved path, you're going to have angular acceleration, and that is manifest in the form of centrifugal force. Going back to this tangent, aberration may be explained as the difference in angle of a beam of light in different inertial frames of reference. So a common analogy is to consider the apparent direction of falling rain. If rain is falling vertically in the frame of reference of a person standing still, then to a person moving forwards, the rain will appear to arrive at an angle, requiring the moving observer to tilt their umbrella forwards. The faster the observer moves, the more tilt is needed. The net effect is that light rays striking the moving observer from the sides in a stationary frame will come angled from ahead in the moving observer's frame. This effect is sometimes called the searchlight or headlight effect. Now, I will mention here really quickly that the sort of infamous experiment Ares failure proved that the Earth is at rest, and it is actually the starlight that is in motion, or it is the inbound light coming from celestial objects that is in lateral motion as it hits the Earth. That's why you have to tilt your telescope to get a full resolution or a full capturing of the light from celestial objects, because the ether is in motion. And what Ares' failure demonstrated is that while I disagree with modern physics' value of the speed of light, it does seem evident that light slows down and refracts through higher density liquids such as the atmosphere, such as water, because of course they're assuming the speed of light in a vacuum. However, in reality, they are not actually taking measurements of light in a vacuum, which doesn't make a whole lot of sense when they're trying to define the speed of light as it would behave in a vacuum. But I digress. Light does appear to slow down and refract towards higher density gradients. So, that does appear to be evident. Although I still hold the position that the value that they have for the speed of light is just absolute nonsense. So we just went into what is aberration, inertial reference frames. Okay, so going back to the original article, sorry for that tangent, but you know, a little background. So we're back to this absurd Romer, 1728, Bradley made another estimate by observing stellar aberration, being the apparent displacement of stars due to the motion of the Earth around the Sun. He observed a star in Draco and found that its apparent position changed throughout the year. All stellar positions are affected equally in this way. This distinguishes stellar aberration from parallax, which is greater for nearby stars than it is for distant stars. What parallax? So to understand aberration, a useful analogy is to imagine the effect of your motion on the angle at which rain falls past you. Okay, so this is just reiterating what I've already sort of mentioned. Standing still in the rain, you're going to get a different effect than running through the rain. So Bradley allegedly measured this angle for starlight, and knowing the speed of the Earth around the Sun, he found a value for the speed of light of 301,000 kilometers per second. So, yeah, that couldn't possibly be anything remotely correct, because the Earth is at rest and the Sun is not some millions of miles away. So, continuing, the first measurement of the speed of light that didn't make use of the heavens was by Armand Fizeau in 1849. He used a beam of light reflected from a mirror 8 kilometers away. Now, just pausing this real quick here, I just want to mention that the light bulb wasn't even invented until 1879. So keep that in mind, because allegedly they're measuring light, you know, using literally torches or some sort of lit, you know, manually lit device, not a spotlight or a light bulb or certainly no laser. And they're supposedly getting 8-kilometer distant measurements. And the way that they did this was rather arcane originally. Very basic, so describing it, it's the beam of light was aimed at the teeth of a rapidly spinning wheel. Now, the speed of the wheel was increased until its motion was such that the light's two-way passage coincided with a movement of the wheel's circumference by one tooth. I'm going to cut to a clip giving an illustrated breakdown of how this experiment was conducted, so you can better understand what they're supposedly using to measure the speed of light.
So Maxwell was all like, hey guys, I think that the speed of light is really fast. I think it's like, well, because he had these constants from electricity and magnetism, I think it's 3 times 10 to the 8th meters per second. And Fizeau, this amazing French physicist who did all kinds of cool things, including some really seminal work on capacitors, in 1850 was sitting around by the fire reading, he was reading Maxwell's work, and he says, well, let's figure out exactly how fast light goes. Now, think about that. How the heck are you going to find out how fast light goes if somebody just told you they think it goes 300 million meters in a second? That means it's going well more than all the way around the world within 1 second. That's going to be a pretty tricky thing to measure. So it's 1850, and here's what he does. He takes a mirror, and it's only like semi-glazed mirror. This is a pretty typical thing that we used in physics. It's a semi-reflective mirror, and that means that some light can get through it, and some light will be bent off of it. So that mirror is sitting right there, and he's going to take that, well, here, look at this. There's a semi-reflective mirror. Okay. He takes it, he ripped it off of a car. Just kidding. And then there's light here. So he has this laser pointer, or maybe it wasn't a laser pointer because it was 1850. It probably wasn't even a light bulb. It was a candle or a lantern in 1850. And the laser light, anyway, comes out here and it goes pew, and some of it reflects off of here, but we don't care about that. But what I'm concerned about is that some of it goes through and passes through this devious device. And the device was like, well, let me kind of draw it for you. It's like this circle, but it wasn't a complete circle. It had these notches in it. which had little holes in them. And let's say that it had 20 holes in it, I don't know, something like that. And it looked like this. So this guy, if you spin it, enables light to get through sometimes. And if I spin it fast enough, you can kind of see through it. Let's see that. Can you kind of see through that? Probably not, because it's kind of dark, but I can, and I can see through it sometimes. Now the beautiful thing is, the laser beam would only get through this sucker sometimes. So let's say the laser beam made it through. But the problem is, the laser beam's gonna hit another mirror. This is a high quality mirror. And the only way that laser beam can make it back, the only way the laser beam can come back is if it happens to pass through another one of the slits. Because by the time that first slit, let's bit a big distance here. Let's make this a long way away. All right, cool. The only way the laser beam can make it back is if it comes through the next, or maybe the second next, or third next of those slots. And if this distance is, I don't know, rooms or 1 kilometer or something, then you'll be able to see, oh, where's the eye of physics going to be in this problem? Let's make a blue eye of physics up here. And we'll say that this is our observer who's watching the experiment with some nice eyelashes. And you want to know if you're going to see the light. So you're beginning to see the light. It was going this way, and it comes back only at exactly the right frequency of spinning this disk. See, if you're spinning it too slowly, then you'd be blocked by, I don't know, this one or that one or that one. And so you spin it really, really, really fast so that it exactly goes through one slit and then comes back through the next. And if you're spinning too fast, then it'll be blocked by this little paddle right here. If you're spinning it too slowly, it could be in any one of those. But he spun it at his maximum possible speed, and he calculated with this distance, and he found, yep, that's the speed of light. Pretty ingenious experiment, if you ask me. He had gears, and he knew very well how precisely he was rotating the sucker, and he managed to get the speed of light to some very good accuracy, backing up Maxwell's observations of just a few years previous. What? His name is inscribed in the Eiffel Tower. Hi, France. Good work. Beautiful tower, excellent guy named Fizeau, and you should go to France if you have the chance, because...
So, I'm just going to mention that I totally disagree that using any such experimental setup, such as Fizeau used, you couldn't possibly measure the speed of light. There's too many assumptions involved. The fact that their measurements more or less coincide with the so-called measurements using astronomical observations and using the assumption that the Earth is in motion, using the assumption of a distance to Jupiter, all of these assumptions going into the original so-called measurement of the speed of light, and now these ground-based experiments which are allegedly able to measure the super duper fast speed of light in a scaled down sense is absurd. You know, if you hand them the speed of light that they claim for argument's sake, there's no way that they would be able to measure it accurately using such contraptions and setups. And again, the fact that these contraptions and setups more or less coincide with the previous measurements using astronomical data tells me that their numbers couldn't possibly be right. So what we just looked at was the the Fizeau method, and the next clip that we'll roll is from it looks like a college class, maybe an undergraduate student is giving a presentation of some sort, but you'll notice that again they do indeed shoot for the numbers that they already believe the speed of light to be, and if they get numbers that are outside of the norm, then they consider it to be bad data. But let's continue on and we'll roll that clip at some point shortly. Now, the speed of the wheel was increased until its motion was such that the light's two-way passage coincided with a movement of the wheel's circumference by one tooth. This gave a value for c, and again, c is the speed of light, of 315,000 kilometers per second. Somehow these people are looking for numbers that are similar to what has already been given by the original Jupiter's Moon's Transit experiment, using the term experiment very loosely. They're using these values as a form of a target.
And still, actually, the answer that my group of students got was worse than the answer Foucault got. So even all that time ago, he got a much more accurate answer than we were able to get. using modern equipment. So this is very impressive.
I would just say that it's highly likely that light is way too fast for anyone to get the the smallest possible measurement or the most accurate possible measurement. So in other words, it's very possible that when you're trying to measure the speed of light, say through the spokes on that wheel or using Focault's method, the light could be attempting to pass through, run its course, although it's impeded by the very mechanisms of the experiment, and so you're going to get a false reading of the speed of light. To assume that they're able to measure the speed of light using such setups is just very, very ambitious indeed.
Okay, so that was the first observation, the first experimental evidence for a finite speed of light. Now later on, experiments got much more sophisticated, and they came up with some new ways to measure the speed of light. Okay? And I'm going to tell you about one of these ways. Fuco was a famous French experimental scientist in the 1800s. He did a lot of very interesting experiments, actually. So I'm going to tell you about this one. This is one he did measuring the speed of light, and he got a very accurate value, 298,000. Okay? So about 1%, less than 1% error. Okay. And the idea is quite nice. You have a light source here, and then very far away from each other, you have two mirrors. Okay, I think in the original experiment it was about 10 kilometers distance between these two mirrors.
I would just mention the fact that you can align two mirrors, 8 to 10 kilometers apart to do such an experiment is, well, they must have been pretty darn good, but it's also good evidence of the lack of curvature on the Earth. And I would also mention that I know that it's difficult to get such alignments with light, even with like lasers, high-powered lasers, from such a distance. And so for them to have made any sort of precise measurement over such distances before the light bulb was even invented is quite astonishing.
And the light goes from the source. It's not really a light bulb. It needs to be a focused source of light, right? So the focused source of light. So in the modern sense, we'd use a laser. He didn't have lasers, so he used some optical tricks to get a focused beam of light.
Some optical tricks to get a focused beam of light.
But anyway, the light source, the light goes to the first mirror. It's then reflected to the second mirror, reflected back to the first mirror, and then you observe it.
Jump around. Jump up and get down.
Okay, so this is somebody measuring the light. Okay, so I'm going to try and explain how the experiment works using this ball. This means you have to be good at catching it. Okay, so in the original experiment, I'll give you the ball. Okay, right, so you are the light source. Okay, I am the mirror, and then I'm the first mirror, and then let's say Yeso, you can be the second mirror. Okay, so the light comes to the first mirror. Okay, it then goes to the second mirror, and then it comes back. Now, if I am stationary, then I just throw the light back, straight back at you, right? But the first mirror, that's me, is not stationary. The first mirror is made to rotate. So as time goes on, I go round and round, right? So if we do the same thing again, I get the light here, and I'm like this, so I pass it to you. Then you pass it back to me. But in that time, when the light goes between you and me, I've rotated about this much, right? And that means instead of throwing the light back over here, I throw the light back at a slightly different angle, like that. Okay. Now, if the speed of light is slow, then I turn through a big angle, right? So therefore, there's a big change in the direction of the light. If the speed of light is fast, then I turn through a small angle, so therefore there's a small change in the angle of light, right? So by measuring the change in the angle, you can calculate the speed of light, okay? That's the idea of the experiment.
Right, but what if our ability to detect or properly measure the smallest change in angle, what if we don't have the ability to measure such a small angle in such a small amount of time, especially the faster you rotate the mirror, the worse this would get. But the point I'm trying to make is that it is a bit arrogant to assume that we would be able to measure the smallest possible angle, because I would submit that whatever the smallest observable angle is, that would be the angle that light would take off the mirror. Because even if it was just a fraction of a fraction of a fraction of a fraction of a second, that you're able to measure the change in that mirror's angle. If there was a smaller fraction still, many fractions of that you're able to measure, that's immeasurable because it's so small, then you have thus incorrectly measured the speed of light, assuming that it is little tiny particles, photons, traveling as a waveform through a given media.
So, okay. So in the next slide, I draw a picture of this. So here's the light source. The light hits the first mirror here, goes to the second mirror, and it comes back. But once it's come back, the first mirror has rotated through an angle of theta. That means the light is reflected by an angle of 2 theta here. Okay? So if you measure the angle 2 theta here, you can calculate the speed of light. The formula is there. We're going to derive this formula now. This is question 2 on the worksheet. So this is the Fuco experiment. So you have in the Fuco experiment 2 mirrors, like this. 1 mirror, 2 mirrors. This one is rotating. Okay. Let's say that the distance between the mirrors is L. Put L in the worksheet. Okay. And the worksheet tells you that L is 30 kilometers. I don't think this is the actual experimental value. I think I just made this up.
I don't think this is the actual experimental value. I think I just made this up.
Okay. Then you have a light source here. Here's a source of light. Okay. And the light comes in, is reflected off the first mirror, goes to the second mirror, comes back to the first mirror. But in the time it takes to come back, the first mirror has rotated through an angle of theta. This. So therefore, the light is not reflected exactly where it was originally, but it's reflected at a different angle here. Angle 2 theta.
It seems obvious to me that the light would have also reflected off of that mirror at a much more acute angle than was measurable.
Okay. And what you do is you observe the light here, and you measure the angle. So the key thing in this experiment is how much time does it take for the light to go from here to there. Okay? Because that determines how much the mirror rotates, which determines the angle you measure here. So that's part A of the question. Find the time that it takes for the light to go from here and back. Okay? And that's very easy, right? Because it's just time is distance divided by speed.
Yes, that is easy, assuming you know the speed of light, right?
The distance is 2L. The speed of light is c. Okay, dead easy. Right. So let's suppose that the mirror rotates at a certain rate, omega. Okay? So omega is the rate of rotation of the mirror, okay, which we know. Then, using that, you can find the angle that the mirror turns through. This is part B of the question. So the mirror turns through an angle theta, which is just the rate of rotation times the time. Okay? But from part A, the time is 2L over c. Okay? And in this experiment, you know everything, right? So you measure the angle theta, you know the rate of rotation, you know the distance between the mirrors, so therefore you can calculate the speed of light. That's the way it works. Okay? So just rearranging, then you get the speed of light is equal to 2 omega L over theta. So that's it. So that's the equation that was on this slide here. Okay, except omega is d theta by dt, and h I've called L. It's the same formula. Okay. Finally, I put some values in and ask you to calculate. Okay. So actually, in part C, I give you the speed of light. I do it backwards. I give you the speed of light, and I ask you to calculate the angle theta. Okay. So I told you that the speed of light is 3 times 10 to the 8 meters per second. Okay. And I tell you that omega is 1 revolution per second. Okay. And I ask you to find theta. Okay. So theta then is 2 omega L over c. And then you know all this. So you just calculate it. And if you do so correctly, you get an answer of 0.072 degrees. So the point of this question was to show you that this is really, really small, right? And even though the distance between the mirrors in this hypothetical experiment was 30 kilometers, right, so it's a very long way, the angle you have to measure is still very, very small. So what this shows is it's a really difficult experiment to do, right? First of all, sending light over such a distance and being able to exactly hit the mirror, and then having enough light to come back and hit the other mirror, that's not easy, right? The further light goes, it gets weaker and weaker, right? Because it scatters off the air and all other things, right? And you have to send it at exactly the right angle to hit this mirror, and then, even if you achieve that, the angle you have to measure is still incredibly small. So it's really, you know, Fuco is a genius experimentalist to be able to pull this off, right? In fact, last year, a group of students at this university tried to do the Fuco experiment using modern equipment. Okay? So we've got some equipment in this university. There's a laser we can use, and then there's a rotating mirror, which it's a very small mirror, but it can rotate 1,000 times a second. So it can rotate very, very fast. Okay? And because the mirror rotates very fast, the distance doesn't have to be so large. Okay? So when the students did it last semester, the distance was only about 20 meters. Okay? But still, it was a really, really hard experiment to do. And still, actually, the answer that my group of students got was worse than the answer Foucault got.
And still, actually, the answer that my group of students got was worse than the answer Foucault got. So even all that time ago, he got a much more accurate answer than we were able to get using modern equipment. And still, actually, the answer that my group of students got was worse than the answer Foucault got. So even all that time ago, he got a much more accurate answer than we were able to get using modern equipment. So this is very impressive.
Loosely. Again, they're using these values as a form of a target. And this is confirmation bias. This is not science, because they get such widely varying measurements. None of their measurements could possibly be anything remotely correct at all, not even close, because they're using theoretical values for the distances, stellar distances, as their starting point. That's sort of their original measuring stick for the speed of light, and all of their other calculations are biased by that presumption. Right, so it's all confirmation bias. So anyway, this goes on to say the speed of the wheel was increased until its motion was such. Oh, read that. So this gave a value for C of 315,000 kilometers per second. Leon Focault improved on this result a year later using rotating mirrors, which gave the much more accurate value of 298,000 kilometers per second. His technique was good enough to confirm that light travels slower in water than air. So I would say that that's probably all that it was good for, because again, these numbers that they have couldn't possibly be remotely correct or verifiable. It's all very much, and we'll get into why it's very much theoretical, but um, their measurements are widely varying. They don't get consistent answers, and they're looking for results that are in line with sort of accepted values. Otherwise, they call it, even to this day, if they don't get values that are close to what these ancient dudes got, then they say that they were getting bad measurements.
And still, actually, the answer that my group of students got was worse than the answer Foucault got. So even all that time ago, he got a much more accurate answer than we were able to get using modern equipment.
But I would argue that you're going to get a wide variance in measurements, because the way that they try to conduct these experiments even today with spinning mirrors and different things is just absurd in terms of thinking that they're actually going to measure the speed of light this way. And again, these ancient dudes back in the 1800s didn't even have light bulbs, still up to this point, for crying out loud.
And still, actually, the answer that my group of students got was worse than the answer Foucault got. So even all that time ago, he got a much more accurate answer than we were able to get.
Continuing on with the original article, after Maxwell published his theory of electromagnetism, which I don't necessarily agree with the, accepted theory of electromagnetism. Sure, in practice and application, there are fundamental principles involved. You spin a magnet around a coil, or spin a coil around a magnet, and you generate an electromagnetic relationship. It's very simple, but what's going on inside at the quote-unquote molecular level is up to very much theory, and that is why they still call it the electromagnetic theory, because while the theory does sort of answer the questions as to what is going on inside of an electric circuit, any honest electrical engineer or electrician will tell you they don't know exactly what's going on inside of a circuit at the molecular level. Of course they don't, and such a thing will probably never be directly observable to confirm, that it is little tiny subatomic electrons that are traveling, from molecule to molecule or from atom to atom in order to give the electric current. That is very much theoretical. After Maxwell published his theory of electromagnetism, it became possible to calculate the speed of light indirectly by instead measuring the magnetic permeability and electric permittivity of free space. Now, this was first done by Weber and Corelodge in 1857. In 1907, Rosa and Dorsey obtained 299,788 kilometers per second in this way. And according to this, it was the most accurate value at the time. I just love the fact that they called these accurate. They couldn't possibly be accurate because it's all based on these values of stellar distances, which couldn't possibly be correct. And then going into measurements that really couldn't be verified as accurate measurements of the speed of light. The speed of light would be so fast that you're talking about light traveling many, many times before their little mirror is able to spin even the slightest fraction of a degree. Many other methods were subsequently employed to further improve the accuracy of the measurement of c, or the speed of light, so that it soon became necessary to correct for the refractive index of air, since c is light's speed in a vacuum. In 1958, Froome obtained a value of 299,792.5 kilometers per second using a microwave interferometer and a Kerr cell shutter. And a microwave interferometer is something like LIGO, if I'm not mistaken. And I know that LIGO is set up to where you have two very, very long cylinders underground, aligned perpendicular to one another, so 90 degrees to one another, and they measure the interference patterns in light waves or microwaves as they go and bounce off the far end of the cylinder many kilometers away, and then join back up at the center where again they are aligned perpendicular to one another or 90 degrees. And that interference pattern is measured to allegedly measure all sorts of things, including the alleged binary black hole system colliding to form a single black hole or a single singularity, which allegedly caused gravity ripples through space-time 1.3 billion years ago, and they just so happened to pick it up on the little LIGO interferometer. But of course, it was probably seismic activity, P waves. Now, this claims that after the 1970, the development of lasers with very high spectral stability and accurate caesium clocks made even better measurements possible. Now, what I will mention is that they're looking for answers that are within tolerances of the original ancient experiments. Otherwise, they would call it bad data if it wasn't close. And again, I think it is quite preposterous that they believe they can measure the speed of light by measuring angles of light bouncing off mirrors and things like that. It really is quite absurd. But by 1970, the point had been reached where the speed of light was known, and I'll say allegedly known, to within an error of plus or minus 1 millisecond. It became more practical to fix the value of c, or the speed of light, in the definition of the meter, and use atomic clocks and lasers to measure accurate distances instead. Nowadays, the speed of light in vacuum is defined to have an exact fixed value when given in standard units. Since 1983, the meter has been defined by international agreement as the distance traveled by light in a vacuum during a time interval of 1 over 299,792,458 of a second, or maybe it's 299,000. This makes the speed of light exactly 299,792.458 kilometers per second. Also, because the inch is now defined as 2.54 centimeters, the speed of light also has an exact value in imperial units. This definition only makes sense because the speed of light in a vacuum is measured to have the same value by all observers, a fact which is subject to experimental verification. Of course it is, because trying to say that they're able to measure the speed of light using these assumptions and experiments with rotating mirrors and such is just quite absurd to me. I'll let everyone can make their own mind up, but it seems to me to be a pile of pseudoscience. Now, here's a PDF I found. Well, I'll put a link in the description. It's another educational college website. Speed of light measurement using the Focault method. The objective of this experiment was to measure the speed of light using the same method developed by the French physicist Jean-Bernard Léon Focault in 1862, decades prior to the invention of the light bulb. The speed of light is one of the most important constants of nature, and of course they claim that it's a constant, but they constantly get different measurements. After Einstein presented the special theory of relativity, it was established that the speed of light is an upper limit to the velocity of any object. And, this is where I diverge wildly with this whole idea of tiny little particles or photons traveling through the air or media traveling light. Our eyes and instrumentation pick up light waves and different types of non-visible waves as well. To even call them waves, to me, I think is a little bit jumping the gun, because it doesn't seem as if we have any real good evidence to prove that light is actually little photons or particles traveling in waves. If anything can travel through a medium that is theoretically a vacuum, then then it's technically it isn't a wave at all. A wave needs a medium to travel through. Light, it seems to me, as opposed to traveling at all, is just something that is emanated from a source and then is picked up by our eye or by instrumentation without any physical transference of little tiny particles of light or objects at all. But instead, it's more of a photo development process that's happening in our eye. There isn't light hitting our eye. Our eye is attuned to the frequency or attuned to the vibrational state of whatever light is and picks up on that through space or through a vacuum or through liquid or whatever. But it doesn't seem to me necessary to have little particles of light or photons traveling through the air or through the water or through the vacuum, in theory. So, throughout history, there have been many attempts to measure the speed of light, such as those by Galileo, Romer, Fizeau, and Focault. In 1638, Galileo proposed having two covered lanterns at the tops of two hills located about a mile apart. After one lantern is uncovered, the person holding the second lantern uncovers theirs. By measuring the time elapsed between the first person uncovering their lantern and when that person sees the second lantern, the speed of light could then be calculated by dividing twice the distance between them by the elapsed time. And by the way, I did want to mention before, it said that these experiments used 8 kilometers away, which is, I don't know, what, about 4 or 5 miles, something like that. And I'd love to know how that was possible on the spherical Earth that's in motion, but anyway. Of course, this experiment by Galileo, because of human reaction times and the greatness of the speed of light in theory, Galileo could only determine that the speed was much greater than could be determined by use of his procedure. Romer was the first to prove that light has finite speed. It is known that the moon would be eclipsed for the same amount of time because he noticed that the eclipse appeared to be longer when the Earth was moving away from Jupiter than when it was moving toward Jupiter. He attributed this to the finiteness of the speed of light. And again, this is assuming that the Earth is in motion at all, which it isn't, demonstrably so. Observations made between 1671 and 1673 were the basis for his calculation. He calculated that the speed of light to be around 2.1 times 10 to the 8th meters per second, 29% error. In 1829, Fizeau designed a method that consisted of spinning a wheel with slits. Light would travel through the slit, bounce off a mirror, and either pass back through the same slit or get blocked by the next slit. Fizeau used specific values for the distance between the mirror and the wheel, the number of slits on the wheel, and the rate of rotation of the wheel to find the speed of light. The speed of light he found was 3.15 times 10 to the 8th meters per second, an alleged 5% error. Now here's a diagram for the Focault method showing the optical path of the laser in the setup. And again they say laser, but I guess this is their recreation. I can guarantee you that Focault did not have a laser back in the 1860s before the light bulb was invented. So there's their laser. So what they're doing here is they bounce light off of a mirror that's rotating and measure the angle that the light bounces off it after, hitting another mirror. And they believe that they can measure the speed of light this way. Now, either the faster you spin the mirror in theory or the longer the distance that the light has to travel, the more accurate the measurement would be, as long as it's a known distance, of course. But the smaller you make the experiment, the faster you have to spin the mirror to get an accurate measurement according to them. Although I would say that they're grasping at straws trying to measure the speed of something that it probably isn't measurable. Um, but to say that they can measure it accurately and throw out data or throw out experimental results that don't fit neatly into the allowed spectrum, that is not scientific. That's just conforming to pseudoscience as a religion or a scientism. And so what is essentially happening is there is this underlying or preconceived theory that the speed of light is something close to what the ancient philosophers and the ancient experimentalists came up with, using all of this asinine theory about the distance to the heavenly luminaries, which couldn't possibly be remotely correct, and then using some half-baked experiments prior to the light bulb even being invented, let alone lasers, to measure the angle or to use different sort of archaic, primitive experimental situations with spinning mirrors over great distances, and then using that as your yardstick or using that as your base to try to match that or get results that are close to that, is the opposite of science. It's pseudoscience. But it is indeed what happens. Any data that's really far out or far away from what would be considered accepted would be disregarded. And to liken light to a physical measurable object, even assuming that the speeds that they are coming up with are correct, to say that that's measurable on a small scale is asinine. I disagree with this entirely. But as long as their answers are within a certain tolerance of what the others have said, around 299, 300,000 meters per second or kilometers per second, whatever the heck it is, it really is quite humorous when you think about it, because what they do is they take these preconceived values that they must sort of match or come close to in their measurements and develop very complicated mathematics around measuring the speed of light using these angles, but it's all based on fallacious assumptions and fallacious principles at the heart of the thing. To be so arrogant as to think that you can measure these angles and somehow derive the speed of light is it defies logic. Especially when you factor in the fact that any data that comes back that is outside of that tolerance zone, they disregard it as bad data or bad results. So here's a good demonstration of how they claim to be able to get the speed of light from such basic experiments. And this sort of experimental layout appears to have plenty of room for error. Again, for example, if the light bounces back so quickly that no measurable turning of the mirror can be detected, then you would see that as a null result, or you wouldn't see that that change in the angle because it happened so fast over such an acute area. Say that there was no change whatsoever at all in the angle of the mirror, that's how fast the light was, then you wouldn't be able to measure that, you see. So in the mid-19th century, again, French physicist Focault made the most accurate measurement to date of the speed of light, using a laboratory-sized apparatus consisting of rotating and fixed mirrors. This method was subsequently improved upon in technique and by scale by Albert Michelson in the 1920s, resulting in the most precise mechanical measurement of the speed of light with an error of only plus or minus 4 kilometers per second, which again I would say that is not knowable. An apparatus inspired by Focault's original technique is accessible as a classroom demonstration or laboratory and makes an excellent way to illustrate this finite but large speed of light. So here's the sort of setup animated. The basic technique is to send a beam on a path so that it bounces between a rotating mirror, a fixed mirror, and back to the rotating mirror for a total distance 2D, as shown in the above illustration. The time of flight of the light on this path implies that the rotating mirror will have turned very slightly between the two times of arrival of the light. This small rotation will deflect the beam of light through a small angle from its original path, producing a measurable effect proportional to the mirror and inversely proportional to the speed of light. If the rotational frequency or revolutions per unit time of the mirror is given by V, then the deflection of angle is given by, and here's the geometry. This is where they dazzle you with long, complex mathematical equations, but at the end of the day, to think that you can measure the speed of light using such a contraption and get anything remotely correct, to me just defies reason. It seems to me that they're using mathemagics to insinuate that they have a viable, cogent answer here, but to me it seems rather absurd. Even if, they make the math work, I don't buy it, especially because it's very close to what the ancient guys got with their estimates using the unknown values to Jupiter. I mean, give me a break. If it's anything remotely close to that, then to me then it couldn't possibly be correct. And again, their answers appear, even to this day, appear to be influenced by what is accepted. And so if they get values that are far outside of what is accepted or acceptable, then they chalk it up as bad data and do the experiment again. And I would suggest that you would get many different answers or many different results using such setups. Okay, so looking at Weber-Corelodge, the 1850s, looks like Weber-Corelodge experiment compared two systems of electrical units. The principle was to discharge a Leyden jar or a capacitor that had been storing a known amount of electric charge in electrostatic units, and then to see how long it took for a unit of electric current as measured in electromagnetic units to produce the same deflection in a galvanometer. The ratio turned out to be very close to the measured speed of light. So we have a coincidence here. This time frame appears to be similar to that of the speed of light, or at least the arrivals at using measurements, half-baked cockamamie experimental measurements to garner the speed of light, resting on all sorts of assumptions and arrogance to think that we can actually measure the speed of light. But because these two figures appeared to coincide, then the electromagnetic theory is that electricity runs, or electric circuits run at the speed of light, which is a pretty wild long shot in my opinion, knowing everything that we've reviewed about how they've arrived at the speed of light insofar. So does that mean that there is a connection, or is this a coincidence that they're getting numbers that are similar? Does that necessarily mean that the two are connected or related? I tend not to think so. Because with electric theory, again, the theory is that you have little electrons traveling across, from atom to atom or molecule to molecule, traveling across these highly conductive materials like copper. But it doesn't necessarily mean that's what's going on. that's never been imaged. You can't see it under a microscope, and it is very much theoretical, as mentioned earlier. And so to assume that there's something in there traveling at the speed of light, or propagating at the speed of light, or whatever term you want to use, is, in an electric circuit, it's non sequitur. You can make that claim, and you can put together a bunch of mathemagic to state your case, but when your experiments are inherently biased towards a acceptable sort of outcome, then you have something that I believe is immeasurable, at least consistently. You're not going to get a measurable speed of light using any of these experiments without a great deal of interpretation and, I believe, data fudging, or chucking away that data that doesn't conform. So Weber interpreted this ratio in connection with the convectively induced force that he believed to exist between two charged particles in relative motion. He believed it to be the speed that would produce an exact counterbalancing force to the electrostatic force. In this respect, the speed of light becomes like a kind of escape velocity, with the convective force being like a centrifugal force. Maxwell in 1862, however, interpreted the result differently. So at the end of the day, it appears to me that the measurements of the speed of light are very, very much questionable at least, and at worst, a big pile of pseudoscientific rubbish. Again, we started with the flagship 1600s experiment involving the transit of the moons of Jupiter, and without knowing the distance to Jupiter or their moons, or things like refraction as well, which we didn't even touch on, that sort of cornerstone flagship yardstick for the speed of light back in the 1600s is 100% in error. I mean, it couldn't possibly even be remotely correct, knowing what we know about the Earth being a stationary plane, and the wandering stars certainly not being millions of miles away. And so any values or figures that they may have gleaned from such experiments would have necessarily been way, way off. Now, of course, when they measure, in quotes, measure the speed of light using local miniature experiments like Focault or Fizeau had done in the 1800s, there's so much room for error. Again, my main problem with any of those physical experiments done by Fizeau and Focault were the fact that light would be so fast. Even with Focault's instance, I think it was 8 kilometers. Even over that distance, light very well could have and probably did bounce off of that mirror or escape through the teeth in the instance of Fizeau. But light would have and probably did bounce at a no degree angle change before it went to any degree of change that was registerable or measurable. So in that sense, I believe that their measurements, and even modern measurements of the speed of light, couldn't possibly be correct. The main reason I say that, even for modern experiments, is because they are very close to the ancient, 1600s and 1800s experiments. So the fact that they are close, even remotely close to those, proves to me that they are wrong. And furthermore, modern experimentalists will use those ancient values as their compass, as their yardstick. So if they get results that are far out of whack with what they're expecting, in line with the ancient results, then they chalk it up as bad data and disregard it. Now, we do know that light travels through different media at different speeds. So in liquids or higher density media, it will slow down and hence refract. So refraction is definitely a thing, and that is measurable. But again, my position is that light is not what we're told in theory. Neither are electromagnetic circuits. So in the case of light, we're told that it is photons, little subatomic particles that are actually flying away from a light source and hitting our eye. And to me, that is just quite absurd. Also, in the case of an electric circuit, they claim that it is electrons that are essentially daisy-chaining their way down the line of the host molecules or atoms. And they're doing so at the speed of light, allegedly. But again, I disagree with that theory entirely, that there may not be such a thing as atoms with protons and neutrons and electrons. Of course, the numbers work in theory, but such a thing will never be imaged or proven conclusively. And so if atoms can't be proven to even exist conclusively, then how could you prove that electrons, many smaller portions of atoms, are traveling along a daisy chain in order to create the phenomenon of electricity or an electric circuit? And so furthermore, to say that that's happening at the speed of light and somehow being able to make measurements and correlating the two, again, that is electric circuit speed and the light speed, is, again, quite absurd. So with that, I'm going to wrap up this video. Thanks so much for joining me. If you'd like to support this channel, you can do so by becoming a patron at Patreon. That's www.patreon.com/themorgile, or direct through PayPal to www.paypal.me/themorgile, or you can email me at themorgile@gmail.com. Your support is greatly needed, and it goes a long way to help me keep making videos. So with that, God bless you all, spread the word, spread the world, and peace out.
Make the earth shake. Make the earth shake. Rock on. Make the earth shake. Make the earth shake.